So everybody again. So let me just remind you what we did last time. So our main goal is to prove the Alon-Boppana theorem. That's what we're going to do today. And what we did last time was to build intuition towards it by analyzing the infinitely regular tree. So let me remind you what we did, what is the Alon-Boppana theorem, and what's the plannings for today. So, okay, so Alon-Boppana. Why doesn't it work? For some reason I can't write. But my iPad is acting up. Let's try again. No, you're not. Okay. I apologize, but there's something going on here. Okay. Okay, now it seems to be working. So let's see. So what's our plan? So we had the, so our goal is to prove the Alon-Boppana theorem. So let me remind you what this theorem is. So we have, so G is going to be the regular graph. Its diameter is delta, which, to remind you, is going to be at least log n if d is small, and the eigenvalues of mg, which, to remind you, is how we denote the unnormalized adjacency matrix. Lambda 1, at least lambda 2, at least lambda n. So what they prove is the following thing that said that with lambda 2, if d is small and the diameter is big, then lambda 2 cannot be too small. Then lambda 2 is at least 2 root d minus 1 minus some arrow epsilon, or epsilon decays like 1 over delta square. Right? So this is sort of what we were going to prove. And unfortunately, there's some issue here with the Apple Pencil, so I need to stop once in a while and charge it. For some reason, it's not charged. I don't know what's going on. So I'll have to stop and pause and talk for a while the Apple Pencil charges, so I can keep using it throughout the lecture. So fun stuff of using, iPad. So this is just remind. This is what our goal is for today. So what can we say about it? First of all, again, just to remind you. So put it here on maybe here on the side. So remark. If G has n nodes, then the diameter is at least log n over log d, right? So really, I mean, you shouldn't really be thinking too much about the diameter. Just think of the diameter as being some large parameters. As a graph, if we keep the degree constant and we make the graph be larger and larger, then the diameter will have to grow. So the diameter is the two furthest away nodes in this graph. So we're only going to use the diameter to somehow control the error. So I mean, the exact dependence of the error on diameter, that's maybe less of an interest to us. Just wanting to, again, just think of the d is a constant. The graph is growing, so the diameter is growing. So that's one thing I want to point out. And the other thing that I wanted to point out is that, again, that we saw last time, is that, if for the d regular infinite tree, so we define what it means to be an eigenvalue. So all eigenvalues are in this strip of minus 2 root d minus 1 and plus 2 root d minus 1. So this is sort of what we've seen last lecture, and we analyzed this in detail. And really, this deregular infinite tree is our model for, like, maybe the best graph, because it's deregular, it has no cycles. Somehow it's sort of, maybe it's a very clean model. And also remember, this was somebody was asking this last time. When we look at infinite graphs, then lambda one, this lambda one corresponding to the uniform distribution of the all one vector disappears. So we don't have to worry about removing lambda one. Like, all the eigenvalues correspond to really what we think about as lambda two up to lambda n in our graph. So the mixing that happens because of stuff orthogonal to the uniform distribution. So this is just a recap of what we've done last time. So maybe, and again, the goal of today is to prove this Alon-Boppana theorem. So maybe before I do that, I want to see if anybody has any questions about any of that, about the definitions, or about anything that we covered last time.
Let me make a comment, maybe, Shachar, about the spectra of the deregular infinite tree, which I think maybe you mentioned last time. We didn't prove, and isn't in the notes, but I'll probably add it, which is that not only do the eigenvalues lie in that range, actually all of that range are eigenvalues. The spectra is exactly equal to that range of values, including 2 root d minus 1 plus or minus 2 root d minus 1. And the way you can prove this is we set up this recursion to analyze the spectra last lecture, and you can show that when lambda is in that range, basically the solution doesn't have finite L2 norm. So it's kind of not in the space, and you end up getting that they are eigenvalues. So I'll probably add this to the notes later if people want to look, but just wanted to note that we can actually get it, that this is exactly the spectra.
Anybody questions? Everything is clear. Again, even if you didn't follow all the calculations last lecture for this deregular infinite tree, I mean, we're not going to rely on that. So sort of what we're doing today is independent, and really the reason we want to show these calculations to is to explain why this 2 root d minus 1 is like a natural number that comes up here. So our proof, so now again, our goal is now to prove Alon-Boppana theorem. And really our proof are going to rely on something called the tree number. So I want to define this. So this is going to be a combinatorial quantity. So we'll define, so let maybe d to be at least 3, and k to be at least 1. So we define, let's call it td2k. So this is a number to be the number of closed walks in TD, which, to remind you, is how we denote the deregular infinite tree. That start and end at the root. Start and end at the root. Okay. Now it doesn't really matter that it's the root, be any node, but we fix one node in this tree, and I mean they're all the same. This tree has a transitive automorphism group, so any node would be fine. But we choose one. Let's call it the root, and we look on counting walks start and end at this root. So let's see some examples. Let's say we choose, let's do an example. And to be concrete, let's think about d equal to 3. So we have a 3 regular infinite tree. So maybe we start here, and we have 3 nodes. Each one of those has 2 nodes. And so on. So let's first figure out what is, first of all, I claim that if I have a walk that starts and ends at the same node, its length must be even. Because every step you can either go down this tree one level or up the tree one level, right? If I want to start and end at the same node at level 0, then there's no other option. I mean, I have to either go up and down, and it has to be an even number of times. Otherwise, by reason of parity, I won't end where I started. So let's see, what is TD2? So T32. So this counts walks in this tree that start and end. So again, we're going to have this sort of special node, this red node. This is where we start and end. And I want to count options of walking in this tree of cycles of length 2. So I claim there are exactly 3 options here. I could go here and back, or I could go here. Maybe I'll use different color. This is one option. I could go here and back, or I could go here and back, right? So I have only 3 options of going in this tree, having a cycle of length 2. Remember, it's not a simple cycle. I'm allowed to go back on the edges. In fact, I have to go back on the edges that came in. But so I have 3 options. What is T3 for? Well, I claim, well, I have 2 different options. I can go, one option is I go down length 2 and I come back length 2, right? So this would give me what? Well, how many children do I have? 6. So it's going to be 6 options, right? Or I could go, you know, I'm getting run out of colors here. Or I would go maybe, you know, down and up one child, then down and up another child, or maybe the same one. So this will give me another 9 options. So I claim overall I have 15 cycles of length 4 that start and end at the roots. And then we're going to analyze this TD2K later. I'm going to prove a lower bound on it, but for now I just want to make sure that you all understand the definition of it. So either something that's not clear about the definition of this tree number. Okay, so why do we want this tree number? Why do we care about it? Because of the following lemma. The lemma says that among all the graphs that are D-regular, the D-regular infinite tree has the smallest number of cycles of length 2k that start and end at the same node. So let's what does it mean? So let G be a D-regular graph. And let V be some node of this tree. Then the number of cycles, or let's say let's call them closed walks, use the same terminology. The number of closed walks in G of length 2k that start and end at V is at least TD 2k. Okay, so basically you must have at least this number. And what's the proof? I mean, I'm going to show you the proof sort of sketch here. And actually one of your questions in homework 2 is to give a detailed proof of this lemma. So what's the proof sketch? I'm going to show you the idea. So the proof idea. So the idea, the general idea that it's TD is what's called is a universal cover. Cover for G. What it really means is the following thing. So there exists a map. Let's call this maybe phi from the nodes of this D-regular infinite tree to the nodes of G, such that, well, the root of the D-regular infinite tree, which is some arbitrary node, maps to our node V, and edges map to edges. So if UV are in the edges of the D-regular infinite tree, then phi U, phi V are, well, it's not the same V, so let's give them maybe another. V was our special node. So let's say U and U prime are not even phi U and phi U prime are in the edges of G. And how do we build this phi? I mean, again, I'm going to show you sort of proof by picture, and you can sort of write it down more formally in the homework. So basically, we just build it, inductively. So maybe we say, so if this is, let's just try to build. So here's my deregular infinite tree. So on, and here's my graph G, and here's my node V. It has 3 neighbors. So we're going to say, well, we're going to map the root to V. Okay, so we did one. Now we're going to take all the neighbors of it and map them to the neighbors of V. So maybe this is going to go here, and this neighbor is going to go here, and maybe now this neighbor is going to go here. And I'm just going to keep going, right? So I mean, so that for this purple one, maybe the green one is one of its neighbors. So maybe now this green one is one of its neighbors. So we're going to also make this green one to be one of the children of this purple one. So we're not claiming this like a one-to-one map, right? So of course, we're mapping an infinite graph to a finite graph. It cannot be one-to-one, but we're claiming that locally, we map neighbors to neighbors. Right, notice, by the way, the purple one already has a red one as one of its neighbors, so we're not going to use this again. So I mean, for example, if this purple one has another neighbor that's going to be called, I don't know, orange, then this one is going to be orange. And so we just do it inductively, level by level, in this deregular infinite tree. And what's the point of doing that? Well, I claim that now so the point is doing that, so now I'm claiming that any walk in TD maps to a walk in this graph G. And in fact, it maps in a way that's one-to-one. So, and this is going to be one-to-one. So that distinct walks in this deregular infinite tree map to distinct walks in G. So in particular, any closed walk in the deregular infinite tree maps to a distinct closed walk in this graph G. So this gives a lower bound on the number of closed walks in the graph G. Now it's only a lower bound because, of course, this deregular infinite tree, I mean, our graph could have cycles that do not exist in the infinite tree. So there could be more closed walks in the graph, but the infinite tree gives us a lower bound, which is going to be good enough for us. Okay, so I don't want to write this in detail, so I wanted to give you some high-level idea for why this is true, and then we're going to leave it to you to fill in the details in the homework. So, and any question? Okay, so how do we talk it? So now we want to do that. So why was it important to us to count walks in the graph G? So now I want to prove, the Alon-Boppana theorem. And we're going to do it by counting walks. But actually what we're going to prove a slightly weaker version. So we're going to prove, let's call it a somewhat weaker version. What we're going to prove is that lambda is at least 2 d minus 1 minus epsilon, where epsilon is going to be also slightly worse, order of log delta over delta. So it's going to be weak in two different ways. Maybe the most significant way that we don't prove a low bound on lambda 2, but we prove a low bound on lambda, which to remind is just a maximum of lambda 2 and lambda n. So it's a weaker lower bound, and also the error dependence of epsilon on the diameter is slightly worse, but that's maybe a much smaller difference. And you'll see why it's useful for us to prove the bound on lambda, not on lambda 2, and so by using the same proof strategy, but in a more careful way, you can get the bound on lambda 2 as well. Okay, so let's do that. Now the idea to do that is going to be a very, it's going to be a recurring idea that we haven't seen in this class so far, but that exists in many times in graph theory, which is to look on high powers of the adjacency matrix, which really corresponds to walks. So let K to be determined later, and somehow the larger K is, we get a better control. And consider the matrix M. So let M also be the adjacency matrix of the graph, such as the note M here. And what we're going to consider is the matrix M to the power 2K. And I'm going to ask myself, well, what are the eigenvalues of this matrix? Well, the ith eigenvalue of this matrix is just the eigenvalue of M to the power 2K, right? By basically linear algebra. So in particular, by the way, notice that because 2K is even, now we're going to lose whether it's positive or negative, right? This is why we get a bound only on lambda, not on lambda 2, because by taking this power 2K, we lose a sign. So we don't know what the sign was originally, but in particular, we could say that, well, lambda 2 of M to the 2K is equal to lambda M to the 2K. So why lambda 2 for M to the 2K? Well, because M to the power 2K has all the eigenvalues being non-negative. We already said this because that all the adjacency matrices, because they're symmetric and real, all the eigenvalues are real. So taking a real number to a power that's even is going to give me a non-negative number. So now I already killed all the negative eigenvalues of M to the power 2K, I only have positive ones. So the largest one that is smaller than lambda 1 is lambda 2, even in absolute value. So the second eigenvalue of M to the 2K equals to lambda M to the power 2K, but we don't know if it came from a positive one or a negative one, which is why we cannot really prove a bound on lambda 2M, but just on lambda M. Okay, so the goal will be to prove a bound, a lower bound, a lambda 2 to the M to the 2K. And we see that the larger we choose K, we get a better bound. So we'll try to choose K as large as we can, so that our proof would still work. So that's our goal. And how do we do it? Well, we've seen one technique, how to lower bound lambda 2. And we're going to use the same technique here, namely that lambda 2 of any matrix, in particular M to the 2K, equals the maximum of what? Of F transpose M to the 2K F over all vectors that are orthogonal to 1, whose norm is 1. Right, so we've seen that by this, that for any matrix, its second eigenvalue, let's say any matrix whose rows and columns are sum to the same number. So the one vector is an eigenvalue, is eigenvector of eigenvalue 1. The second eigenvalue is characterized by maximizing over F transpose matrix F over all the vectors orthogonal to the first eigenvector, which in this case is all one vector. So we can use exactly the same characterization for M to the 2K. So since we're trying to prove a lower bound, really what we should do is find an F, a vector F, where this is going to be big. Now, before I do that, I just want to point out one thing, that why do we look this M to the power 2K? And what's the relation to walks? So what is this matrix M to the 2K? So if I look on this matrix between two nodes, U and V, its value is exactly going to be the number of paths between U and V in the graph of length 2K. Right, when I take the adjacency matrix, counts edges. And if I take powers of it, it exactly counts paths in this graph, right? So we're going to, now you already see the connection between looking on paths in this graph and looking on powers of the adjacency matrix. So now in particular, we're going to use the assumption that the graph is large diameter to choose F and K in a judicial way. So we assume that the diameter of G is some delta, So there exist nodes S and T in the vertices of G, such as the distance in G between S and T is exactly delta. So I'm going to choose the two furthest away nodes in this graph. And I will define the following function. I call this function fst. So it's going to be 1 on the node S minus 1 on the node T divided by root 2. Okay, that's going to be my function. And I'm claiming this is going to work for us. So what is again this function? So it's a function that has 1 and 1 coordinate, or after this 1 over root 2 in some coordinate, minus 1 over root 2 in a different coordinate, 0 everywhere else. So in particular, you can notice that it sums to 0. So it is orthogonal to the all one vector. So it is a legitimate function we could use to try and lower bound the second eigenvalue. So we can get that the second eigenvalue of m to the 2k is at least this fst transpose m 2k fst. Also notice this vector, this function has exactly L2 norm 1, right? The sum of the squares is 1. So now what we want to do is to analyze this quantity and also to choose k. So let's do this. So what is this bound? Well, fst is 1s minus 1t. So we can write this as, right, it's going to be 1s minus 1t m 2k 1s minus 1t, maybe here we transpose, divided by 2. Right, just plugging in this function we chose. And what is this? So let's see, remember, what does m to the 2k does? It counts patterns. So this is going to be equal to the number of patterns of length 2k. Also, let me do it this way, just in this way. I'll say it in words. It's going to be 1s m 2k 1s plus 1t m 2k 1t minus twice 1s m to the 2k 1t divided by 2. In the last term, I use the fact that m is symmetric. And now, again, remember, what does the m to the 2k does? It counts pattern. So the first term here, 1s m to the 2k 1s, counts closed cycles in this graph that start and end at s of length 2k, which is exactly what we analyzed before. This is the counting closed walks in a graph. Similarly for 1t m 2k 1t. What about this last term? The last term is minus something. We're trying to have a lower bound. So ideally, we should only have positive quantities. So this counts path of length 2k that start at s and end at t. But remember, we assume s and t are very far apart from each other. They have diameter delta. So I want to choose k small enough so that 2k is less than the diameter, so that there are no paths in this graph of length 2k between s and t. So this would allow us to kill this last term. So let's do that now. So let's set k to be delta minus 1 over 2, rounded down. So 1s m2k 1t is 0. So again, what did we do here? We said path in this graph of length 2k between s and t. So by choosing k in this way, we are able to kill this last term. So this last term now just kill.
Shahar, I think I don't know if others experience this, but you cut out for like 10 seconds or something. So you might want to repeat the last like 2 sentences.
Okay, sure, definitely. Yeah, my internet here is not very good. Yeah, so what I said is that this matrix m to the power 2k at entries s and t, right? This is just the same as m 2k at entry st. This counts the number of paths in G length 2k from S to T. But because S and T, their distance is more than 2k, there are no paths in this graph between S and T. So this value is 0. Right? Now also, what about the other terms? So this lemma that we had, the lemma that we had, it also tells us that 1s, suppose M2,
I guess we'll wait a little bit, and if he doesn't come back, I'll take over the lecture, I guess. Let's wait a little bit for him to rejoin. Maybe I'll email him to see if he what's going on if he doesn't join back. All right, I'm gonna wait a little bit to see if I hear back from Shachar, and I guess if not, I'll maybe try to finish the proof of Alon-Boppana. I guess let me look at it quickly. I think we were almost done, so. I really hope he's not just like sitting there lecturing and it's like frozen on his screen. He says he's restarting his computer. Okay, so we'll wait for him to. If it doesn't work, I'll take over. Otherwise, hopefully he'll be back. Okay, there seem to be more substantial technical problems, so I guess I will try to finish this proof and do the rest of the lecture. Bear with me because I was not planning to do this. But we were almost done. Oh, Shahar's back.
Okay. Okay.
Okay.
Hopefully it works next time. Yes, everybody. Yeah, I thought my internet is bad.
I was saved by the bell.
Yeah. See if the screen share works. Oh, nice. Everything works. Perfect. Good. So where were we? So what we did so far is argue that by choosing k small enough so that 2k is less than the minimal path length in S and T between the distance, we kill this last term. Now we just have to worry about the first two terms, right? This term and this term. Now both of them count paths of length, closed path of length 2k in this graph. So the lemma we said this is going to be at least as large as this number for this deregular infinite tree. Right? This is a lemma that we sort of sketched the proof of before that you're going to prove in detail in the homework.
It should be at least as much as this times d minus 1 to the k, right?
Oh, sorry. No. No, this is counting inside the deregular tree. This is not a Catalan number.
Ah, okay.
Yeah, we'll get
we
to
had
that.
we had the d minus 1 to the k before then in the lemma, I guess.
No, the demon. Okay, the demons of the k is going to come once we lower bound this. Okay, so overall, so we can apply this for both of these terms. So we get the same lower bound for both. Now the average is the same. So overall, what did we get? So far, so what do we know? So we know that this the second eigenvalue of m to the 2k is at least as large as t d 2k. So this is sort of the main conclusion of what we proved so far, which is already good progress, because now TD2K is some combinatorial number that does not depend on the graph, right? It's just some number depending on the deregular infinite tree that we want to lower bound. If we can do that, we want to plug it in, take powers, and then, just to remind you, this is the same as lambda m to the 2k. So we take this number, take the 2k root of it. Hopefully that's going to give us a bound that we want to get. Okay, so now we're going to go to do the combinatorics. So now it's going to come the part related to what Max was saying. How do we lower bound this? So again, let me draw a picture here. Let's try to build now an understanding of this number. So we have, or maybe it's too much. Maybe hard to draw. Let me choose D to be 3 again. So we're going to have here, again, remember, we want to count walks in this deregular infinite tree that start at the roots. So this is our root. And we have, the root has 3 nodes, or in general, D nodes. And each one of its children has D minus 1 nodes, and each one of their children has D minus 1 nodes, and so on. How do we count pattern here? So we want to lower bound TD2K, which counts, walk that start and end at the root. I think that maybe we go here and then back, and then you go maybe down here and here and here and down again, and something like that. Some walks here. So to do that, what we're going to do is we're going to define what's called a pattern of a walk. So let's think that the V0 up to D2K be a closed walk in TD, where remember that we start and we end at the root. So I'll define a pattern of it. So its pattern is going to be the following. So note that every step here that we make either gets us further away from the root by one level or closer to the root by one level, right? At every node here, like for example, take this node here, this orange node here, I can either decide to go down. I have d-1 options to do that, or I can decide to go up and have one option to do that. So every step I can think of its pattern and saying, do I go down or do I go up? So its pattern is going to be a sequence is sequence in -1, 1 to the 2k that indicates if we go up or down in each step, right? So we have 2k steps. So we're going to have a sequence of length 2k. What can we say about this sequence? So first of all, so we're going to do two things. We're going to count how many sequences are we going to have that are legal, and given a sequence, how many paths correspond to this sequence. So we're going to have two things. So one thing is we're going to count patterns. And the second thing that we're going to do is count walks per pattern. Okay, let's start with the patterns. What do we know about these patterns? Well, there are sequences of plus, minus, and minus 1. Let's start and end as a root. So let's say P in -1, 1 to the 2k is a pattern. So we know two things about it. We know that it sums to 0. So the sum of Pi is 0, I from 1 up to 2k. Because we're going to start and end at the root. So the number of up step and down steps should be the same. So it's balanced. That's one thing we know. The other thing we know is that we can never go above the root, right? To go here. You can go down, you can go up, but there is no way to go up above the root. So what it means, any prefix of it, if I sum it, it can be 0, it could be positive, but it cannot be negative. So if I look on the sum Pi, I from 1 to j, is going to be non-negative for every j. And I claim that any such pattern is in fact a valid pattern. So turn out that, so what we want to count is sequences in plus minus 1, length 2k, such that if I sum all of them, I get to 0, but any prefix, if I sum it, it's going to be non-zero. Turn out that these patterns actually have a name. They're called, I think, Dick patterns, Dick something, Dick words.
They're Dick paths or ballot sequences. There are a couple.
Yeah, these have been studied a lot. They're called Dick patterns, I think, or they have Dick something. So they've been studied a lot in combinatorics. And in fact, their number, so maybe let me try to just create more space here. Okay, good. So the number of such patterns turns out to exactly be equal to what's called the Catalan number. You can see K or 2K. I don't know how it's usually called. Let's say 2K, but maybe it's going to be K. I don't know, whatever. So this is sort of been widely studied in combinatorics because they come within many applications, not just in our application. And in particular, people have figured out that there is actually a very nice recursive formula for this, and this actually equals to 2K choose K divided by K plus 1.
I think it is CK, by the way. It doesn't matter much.
So this is usually called CK. So the length of the sequence is 2K, but this is called the kth Catalan number. And this kth Catalan number counts many other things. It counts trees. It counts. I mean, it comes up in many different applications in graph theory, in other places in combinatorics. So it's been widely studied. In fact, one of your questions in the homework is to actually give a proof of this bound. And there are different ways you could do it. I mean, the easiest way or the most straightforward is by induction, but there are other techniques to do it. So I mean, we're going to leave it to you to figure it out. So we know this number. Okay, that's one thing that we know. The other one is counting walks per pattern. So what does a pattern tells us? You either walk down or you walk up the tree. If you walk up the tree, you can go back to this picture here. Going up the tree, there's no choice. There's just one option of going up the tree. Going down the tree, I have options. If I'm at the root, I have D options of going down. Any other node, I have D minus 1 options of going down. So overall, going back here, the number of walks per pattern. So pattern is always going to have k steps going down and k steps going up. Again, the k steps going up have no freedom. They have to go up. But the ones going down, you have either D or D minus 1 options. So either way, that's going to be at least D minus 1 to the k. Okay, so overall, what do we get? Overall, we got this lower bound, that's TD 2k, with at least the kth Catalan number, which equals to 2k choose k divided by k plus 1 times D minus 1 to the k. Right? So this was a lower bound we proved. And we know that lambda of n, which is lambda 2 of m to the 2k to the power to the root 2k, is going to be at least this number to the root 1 over 2k. So now we just have to do the calculation and see what bound we get. Right? So we've done all of our preparatory work. We got all the calculations, all the formulas done. Now we just have to plug in the values and hope for the best. So let's do that. So first, let's get some simple lower bounds here. Okay, that's going to be our last step in the proof. So, well, what is 2k choose k? You know, by String approximation, well, this is roughly 2 to the power 2k. But concretely, this is at least 2 to the power 2k divided by root k up to some constant here. So this you get from String approximation. But I mean, the exact approximation doesn't really matter because if it's 2 to the 2k times some lower order terms. So overall, what do we get? We get that lambda m is at least, we get 2 to the power 2k times d minus 1 to the power k divided by, let me just move the constant here so it's more convenient. Some constant. And then we have the root k and we have another k plus 1 here, so it's going to be k to the 3/2. Maybe change the constant a bit. All this to the root 1 over 2k. And this is it. The numerator is really nice. The numerator gives me exactly what we're trying to get. 2 root d minus 1. And we divide by something just right here, but it's going to be times 1 over some constant k to the 3 over 2, but all of that raised to the power 1 over 2k. And that's going to be our error term. That's going to be our 1 minus epsilon. And you see the larger k is, that's going to be closer and closer to 1. So the last thing that we have to do is sort of figure out how does epsilon depend on k. Remember, k depends on our minimal diameter. K was, I'm just reminding you, k was about the diameter over 2, up to the plus minus 1s. So the larger the diameter, the larger we can choose k. So how large can we choose k? And well, so how does the error epsilon decays as we increase k? So that's the last thing we have to figure out. So let's just calculate that and we'll be done. So you want to calculate the last piece of puzzle. So now we want to estimate the error. So again, what we have here is copy it here. So we have 1 over c k to the 3/2, 1 over 2k. So what is this? Just write as an exponential. So this is going to be exponential in, you know, something, maybe some other constant, log k over k, right? So this 1 over 2k is this 1 over k in the exponent, and the 1 over poly k becomes log k in the exponent. And we know that, in fact, it's going to be a minus here because it's 1 over something, it's less than 1. And we know that e to the minus x for any x is going to be at least 1 minus x. That's like the first order approximation, Taylor approximation of e minus x. So all of that is going to be at least 1 minus some constant log k over k. So if we call this our error epsilon, we get that epsilon is order of log k over k. And because our k was a diameter over 2 roughly, it's going to be order of log the diameter over the diameter. And this finishes the proof. So, okay. So just okay. What are the main ideas in this proof? So first of all, we said, well, we want to bound lambda of a graph. So we can do it by bounding lambda to the high power of this graph. High power of this graph corresponds to counting walks in this graph. Because our graph had 2 faraway nodes, we could choose, say there is no short walk between them. So we could use this to define a vector FST. There was 1 here, minus 1 here, well, normalized so that the sum of the scores is 1. So that 1 over root 2 here, minus 1 over root 2 here. And we calculated what bound this gives me, what lower bound this gives me a lambda 2. That was exactly corresponding to this 3 number. We estimated this 3 number, or we lower bounded it, and we plugged this into the formula. So this was the idea. And sort of you see the bound that we get, I mean, if we ignore this error term for a second, is exactly this 2 root d minus 1. So this number now we saw it in 2 different ways. It comes from counting walks in the irregular infinite tree. It also comes from analyzing its spectrum more directly, and that is the right number. Okay. Any questions on this proof? Okay, so the last thing I want to do today is to tell you about graph that actually achieved this bound. That's going to be our last topic for today. These graphs are called Ramanujan graphs. Okay, so let me first give the definition. So a deregular graph G is called Ramanujan if it is optimal in terms of its spectral expansion. If lambda 2 of G is less than 2 root d minus 1, again of the unnormalized adjacency matrix. So really it is the best we could hope for. So we know in general that you cannot be much less than that. If the graph becomes bigger and bigger and bigger, you must approach this number. It cannot be anything less than that, you know, in a way that depends just on D, but it could be slightly less than that in a way that depends on the graph. So as the graph becomes bigger and bigger, you can approach this number. And the graph is called Ramanujan if it really is at most this number. So first of all, one question is, why do we call this graph Ramanujan? And I don't know the answer for that. I don't think Ramanujan, I think Ramanujan sort of lived like 100 years before this notion was even defined. So, you know, he studied mostly number theory, and I'm guessing there are some number theory connections why this is called Ramanujan, but I don't know what they are. So actually, if somebody can figure this out, that'd be interesting to know. But anyway, that's the name that I'm not sure who
suggested. From the Ramanujan-Peterson conjecture, which is used in the, I guess, original constructions of the graphs.
Oh, but I think it is true that Ramanujan never studied expander graphs. Never defined this notion. But anyway, that's a name that stuck. And one thing you could ask you, well, is this in other such graphs? I mean, we proved that, you know, for the infinite tree, we reach this number, but maybe finite graphs can never reach this number. Maybe finite graphs are going to be always twice as worse. So the first question that you want to ask, what you see definition is, are there such graphs? Or maybe this definition is empty. I mean, it has been in the past, in mathematics, people have defined sort of, empty definitions. It just sometimes might be hard to prove that they're empty. So is this an empty definition? By the way, if you have time, then I'll tell you the story of the Mashlerians, which is an interesting story. Which is an example of such an empty definition. So surprisingly, this definition is not empty. And the first example people know is something called the LPS graphs. So Lubotsky, Phillips, and Sarnak. This was, I think, 90s, I guess. When was it? Max, do you remember when they did it? I think it was, 90s, maybe a bit later.
I think it's 90s or late 80s.
Or like 80s, okay, early 90s, late 80s. So they constructed such graphs. And what I want to show you, remaining maybe 15 minutes, is the construction. We're not going to prove it because it's super complicated. It's based on like deep number theories that I know nothing about. But it's an example of an algebraic construction of expanded graphs. And we've seen some examples before. We've talked about Cayley graphs. We talked about the generalizations, Schrei graphs. And in fact, many of the original constructions of these graphs were all algebraic. And so let me tell you about the construction, but also I want to tell you that, only much later, people were able to figure out non-algebraic constructions of even expanders, not necessarily Ramanujan expanders, just any expander with a noticeable spectral gap. And what we are going to show you, starting the next lecture, is first of all, well, not their construction, but a related construction by Margulis. So again, the first proof was using deep number theory, but then there was a follow-up work by Gaber and Galil that gave an elementary proof of the same construction. So we're going to show this to you. We're going to teach that to you. Because this proof uses nothing that's sort of beyond basic, some basic geometry and combinatorics. I mean, it's sort of elementary, but it's motivated by this algebraic construct, this number theory, I would say, explanations. And also we're going to teach you something called the zigzag construction, which is a completely combinatorial construction, very different than the algebraic ones. So you're going to see two very different constructions of expanded graphs, but not Ramanujan. So constructing Ramanujan graphs is much harder. Nowadays, there are a few constructions known, but in general, this is still widely studied. So what is the construction? So now I want to tell you about this LPS construction. So LPS stands for Lubotsky, Phillips, Sarnak.
It's 88, by the way, I think.
88?
LPS. Yeah.
88. Okay. So the construction is going to be the following. So let P be prime. They will construct the regular graphs, the regular Ramanujan graphs for D equals to P plus 1. So the construction is not for any degree. It's only for prime plus 1. Only for this specific parameter the construction works. Later, so this was generalized later to some prime powers plus 1 by Morgenstern. Okay, so there is a generalization replacing primes with prime powers, but again, this will not work for any degree. So it's only for specific degrees. And what to define the construction is a bit of algebra. Okay, let's see. So first of all, we need some definitions. So the first definition is what's called GL2. Okay, first of all, before that. So we will need, okay, let's do that. So I need, so FQ be prime finite field. So just all the numbers from 0 to Q minus 1, modulo Q. and GL to FQ, that's called the general group. That's going to be all the 2x2 matrices over FQ, which are non-singular. So they're, invertible, although the determinant is non-zero. So this is just what's called the general inner group. So all the 2x2 non-singular matrices. And what we actually need to work with is a quotient of it. It's called the projective general inner group. So it's going to be a quotient of it. So it's going to be a quotient of GL to FQ, where we identify matrices A and B if they're the same up to a scalar, if A is alpha B for some alpha in FQ. Okay, so that's just a starting point. So we start with having all the 2x2 matrices, but then we want to say if two matrices are the same up to a constant, multiplied by a constant, we identify them. And that in general you can do for groups. And this gives you what's called, it's not a subgroup, it's a quotient, but you can prove this is still a group. And that's called the projective general inner group. That's going to be the group in which we're going to operate. And then I need two facts from number theory, which are sort of classical facts in number theory. So fact one. So let Q be prime. We want to ask that when there exists an I in FQ such that I squared is -1. So when there is an element in FQ, which is the root of -1, and it's a classical theory that this is if and only if Q is congruent to 1 modulo 4. So if the prime number is 1 modulo 4, then there is an element in FQ whose square is -1. That's if and only if. Okay, that's one fact we'll need. The second fact we'll need is something that's called Jacobi four-square theorem. And it says the following thing. Let n be at least 1. The number of ways, the number of distinct ways to write n as the sum of 4 squared, like a squared plus b squared plus c squared plus d squared, has a very nice formula, equals the following thing, 8 times the number, the sum of all the divisors of n. Yeah. Okay, so it's again, it's a fact in number theory. It said, first of all, any number can be written as the sum of 4 squares. And actually, there's a nice formula for the number of options of doing it, which is exactly you sum all the divisors of n. So all the number of n that divide n, and you multiply by 8. And in particular, what we'll need, so in particular, if n is prime, no, so it has only 2 divisors, 1 in itself, then this number is 8n plus 1. Yeah, that's going to be another fact we're going to use without proof. Well, in fact, we won't prove anything here. So now what is this LPS construction? So let PQ be primes. But we'll assume a few things about them. They're going to be completely different. So not the same prime. And also P and Q are going to be congruent to 1 mod 4. So we can apply this fact 1 we had. And let's fix some element I in FQ such that I squared equals -1 in the field FQ. So I squared is congruent to -1 mod Q. And we define the following set. So S is going to be a set of matrices, 2 by 2 matrices, the following form: A0 plus I A1, A2 plus I A3, minus A2 plus I A3, and A0 minus I A1. And what are these numbers? A0, A1, 2, they're integers. So A0 squared plus A1 squared plus A2 squared plus A3 squared is exactly how we want to write this number P. And then we're going to put some extra condition on them to break some symmetries. So A0 is positive, it is odd, and all the rest are even. A1, A2, A3 are even. Okay. So again, let me just, okay, before, okay, so what is this? So first of all, notice these numbers are not modulo Q or modulo anything, they're just integers. But the matrices, we use them to define elements in the field FQ. Okay. So so first of all, so here's the facts. The side of S is going to be exactly P plus 1. If you remember, this Jacobi theorem told you that just counting this, the number of options of doing that, writing P as the sum of 4 squares is 8 times P minus 1. And they added this condition just to break symmetries. So it tells us every option has like which one is odd, which one is even, which one is positive or negative. So this sort of breaks all the symmetries. So this exactly gives you P minus 1, not 8 times P plus 1. And what the construction is the following thing. So the construction, so the graph that we're going to choose is a Cayley graph, where the group is going to be this projective general linear group, 2 by 2 matrices over FQ, where the generators is being S. So I'm just reminding in general, which is a Cayley graph of any group with any S. This is a reminder here. So reminder, G is a group, S is a subset of the group, which is the same as its inverse. So every element S, also its inverse is there. Then the Cayley graph is a generic way of defining algebraic graphs. So its vertices is all the elements in the groups, and the edges are going to be, you start from a group element and you multiply with some elements from S. So this is always a generic way of defining algebraic graphs, what's called Cayley graphs. And what Lubotsky, Phillips, and so on is define a very specific, concrete, explicit Cayley graph. And the main theorem is that this graph is Ramanujan. So this graph, the degree of this graph is P plus 1. You can verify that S is in fact, if a matrix is in S and its inverse is also there. And the main theorem that we're not going to prove, but that G is, well, it's going to be D, which is P plus 1 regular. That's not hard to do, to verify, but is Ramanujan. That's a deep theorem here. So it's second eigenvalue, towards D minus 1. Okay, again, we're not going to prove anything on that. Let me just tell you a few more facts about Ramanujan graphs. So a few facts. So one thing is that you could ask, what about random graphs? We know that random graphs are going to be expanders. Our random D regular graphs are going to be Ramanujan. Well, we don't know, but we know it's close to it. There's actually a very remarkable work by Friedman. And it shows that, you know, if you fix D, take n large enough, and you take a random D regular graph G on n nodes. So you just take n node, you choose a random D regular graph from all the possible ones. Then with high probability, lambda 2 of G is going to be less than exactly 2 root D minus 1 plus epsilon. So you know epsilon goes to 0 as n goes to infinity. So at least random sparse graphs are close to Ramanujan. They don't quite hit this number, but they get closer and closer. And this is considered to be like, you know, a tour de force. It was a remarkable, like a 100+ page paper, very detailed, very complicated. People have somewhat simplified some parts of it, but still consider very, very complicated results. And recently, there have been several works that were able to use different techniques to construct Ramanujan graphs for values of D, which are not just prime plus 1, but other values. So far, people don't know how to do it for graphs, but they know how to do it for bipartite graphs. Which is, you can also define Ramanujan bipartite graphs. And now there are constructions, other constructions of such graphs, which are not algebraic. But again, this is still, to a large extent, a very active area of research. People are still discovering new things all the time. Okay, so this basically completes our chapter on optimal expanders. So we've sort of proven the Alon-Boppana theorem, giving us exact tight bounds for, you know, given a D regular graph, what's the best lambda we could get. We saw that this lambda is obtained by the D regular infinite tree, and we saw that, you know, the main ways to prove it is to basically do combinatorics on this D regular infinite tree and connect it to counting closed walks on graphs, on irregular graphs. Any questions? Okay, so again, what we're going to start doing next week is we're going to start seeing explicit constructions of expanders, and we're going to see first an algebraic construction by Margulis with an elementary proof by Gaber and Galil, and then we're going to see the proof of the zigzag, well, the construction of the zigzag graphs, and which is going to be a very different, very combinatorial construction. Okay, so I guess that's it for today. So no more questions.
I know one of the main expander constructions actually sometimes just gives you a multi-graph instead of a simple one. Is this that construction, or is this different?
Yeah, that's a good question. I mean, in general, for most applications, we don't really care if the graphs are simple or not simple. If we could allow multiple edges, that's not usually a problem. Here, I think this construction actually gives you a simple graph, just because you won't get the same matrix twice, the same generated twice. In general, Cayley graphs are going to be simple graphs.
Okay.
Construction, and I think that the zigzag one would also give you simple graphs. But usually, for many applications, we don't really care if they're simple or not.
Okay. Thank you.
The Margulis one, the one we'll cover on Tuesday, will have multi-edges.
Okay, that's nice.
Although I'm guessing that because we're not trying to get optimal bounds on lambda, you could probably make it into a simple graph by slightly changing lambda.
That was going to be my follow-up, but I was gonna wait till next week. But yeah, okay.
Perfect.
Gotcha. Thank you.
Okay, so now let's maybe finish for today. So I'll stop the recording and see you all next week.
Thank you. Thank you.